The final lectures of this semester, which are numerical methods 2. So yeah, let's see, here we go. So what we're going to look at is a rod insulated at all points except at its ends. So you consider kind of a heat sources or heat sinks at either end. And it's if the rod is very, very narrow with respect to its width and its length, if it's basically like a wire, then it's essentially, you can kind of consider it a one-dimensional object. Now it's insulated. Now it's not insulated here. I don't really know how to draw that. Something like that. But it is insulated from the air. So the air temperature here doesn't actually matter. Okay. So what we're going to do is we're going to see if we have an initial temperature distribution of the rod. So for example, if the rod is initially 0 degrees, how does the temperature change as the temperature starts moving, as it were, towards an equilibrium temperature? Because that's essentially what happens. Various different arguments you can talk about. So things go into thermal equilibrium. Now, maybe they don't have enough time before something happens, but that's the basic idea. So we're going to zoom this out, as it were, a little bit. So we're going to make this three-dimensional now, because it is actually three-dimensional. Now, as I try and draw this, it could get a bit whack. Okay, I'm going to totally just exaggerate the dimensions of it. So we've exaggerated the dimensions. Yeah, okay. So take a little volume element. So take a little slice of this. Now it'll be a little cube, but remember, the delta x and delta y and delta z are very, very small, and essentially kind of, yeah, like a very, very, very narrow square wire, but with square cross section, but that makes this piece very, very small. Okay, so this would be probably delta x, this would be delta y, and they should all be equal, and then the width would be delta z. So this volume here has, well, it refers to that little cube, but its volume is length by width by height or whatever. Okay, so when in steady state, the problem is quite easy to analyze, and I think that's what we're actually going to do now. So imagine that the rod is in steady state. We probably have to write down two other things here, that the temperature at 0 is equal to T1. So that's the temperature of the heat source or heat sink on the left, and on the right, where L is the length of the rod, let's call this T2. Okay, so we're going to analyze it when it's in steady state. And it's actually very, very easy. So when it's in steady state, the heat in equals the heat out. Now I'm going to write down 2 points here. This point and this point. Now this is the point x, and this is the point x plus delta x. And because the dimensions are, because it's a very, very, very thin rod, essentially the heat flux can only flow in one direction. Now the way we're doing it, you can imagine the heat flowing from left to right, but if it's actually going from right to left, we're going to have, the things I write down are going to be two negative things. Actually, it doesn't really matter what direction it is, but I'm imagining that it's hotter on the left, so the heat is going this way. Okay, so we have that if it's in equilibrium, we would have argued this in the previous lecture or two, that the heat in must equal the heat out. If there's more heat going in, then the temperature is rising, and when the temperature is changing, that's not thermal equilibrium. So in thermal equilibrium, temperature is constant. There is still heat flow, but it's done in an equilibrium kind of way, that the heat flow in equals the heat flow out. So the total amount of heat in the delta V stays the same, so the temperature stays the same. So how does this heat flux density work? Well, it's joules per meter squared. So you multiply the heat flux which in this case would be Q at X, by the area of that face there, which is delta Y by delta Z. And then you look at the heat flux at the other side, and it's the same area, you get this formula here. Divide both sides by delta V, and now am I missing delta T? Oh yeah, I'm missing a delta T here because there has to be some time for the heat to flow. Okay. Now divide both sides by delta V delta T, and you end up with this equation here. And as the volume gets smaller and smaller and smaller, well, that's the same as saying delta X is smaller and smaller and smaller. And of course, look at that thing, that's a derivative, isn't it? So you end up with the partial derivative of heat flux density with respect to X is equal to 0. Okay, and then Fourier's law, now that Qx there is its notation for that. So, no, that's wrong. Sorry, my apologies. So what this is this is very bad notation. This is heat flux density is proportional to the difference in temperature. So when you got a hot bit and a cold bit, you'll get a flow of heat from hot to cold. That's what this formula here says. So using Fourier's law, differentiate both sides of this, you'll get that the partial derivative of heat flux density, and then differentiate the right hand side with respect to X partially, minus K times the second derivative of temperature. So I've differentiated both sides with respect to T of the previous thing, and look, we've actually shown above, so combine these two, that partial Q partial X is in fact equal to 0. And then you've got the thing on the right equal to 0, divide both sides by minus K, we get the 1D Laplace equation, that the second derivative of the temperature with respect to distance is 0. Now what is the solution of this? So those of you who kind of understood what was going on with Euler's method and the error in Euler's method and what thing has a second derivative of 0, it's a line. So the solution of what has a second derivative of 0 is a line. So we know that the temperature is a line, and it goes from, okay, instead of T0 and T1, so yeah, T0, T1. Yeah, we'll just draw the picture on the next page. So we have at 0, the temperature is T0, and at L, the span of the rod, the temperature, say, is T1. And the temperature goes like this. It just, it grows linearly. It wouldn't be too difficult for students like you to write down an equation for that. What will it be? Y equal to M. Rise over run is T1 minus T0 over L. X plus C is T0. So what's that saying? It's saying that if you go back and think about the rod, so this one's going from cold to hot. So I'm going to draw some. So this is cold, and the other side is a bit warmer. Okay. Now the heat is flowing from one side, from right to left, but it's working in such a way that the temperature is increasing in a linear way. So if you look at what's happening with the temperature, if you go across, say, one unit of distance, the temperature will increase a certain amount, but it'll keep increasing at the same rate. Like that's what a line is. The rate of change is constant. Okay, so that's the easy situation. So now suppose that the rod isn't in steady state, and this is a bit harder. So, and I think I've written some of it for myself below. So let's draw our picture again. So here, let's draw our volume element. So you got heat. Now the way we drew it, it doesn't really matter which way you draw it, because if you draw it the wrong way around, like here, I'm saying like this, the heat flow is actually going the other way, the way I've drawn it, because it should go from hot to cold, but it doesn't affect the equations because they both be minus or whatever. So I'm just going to draw them this way. So I'm going to say this is the point X and this is the point X plus delta X. Okay. So the heat in would be Q of X times the area now, if you go back, would be delta Y, delta Z, and then the time is delta T. That's the heat going in. And what about the heat going out? Well, it'd be Q of X plus delta X, because the width of the box is delta X, times delta Y, delta Z, delta T. Now, what about, so we're saying that the difference between these is the amount of heat that is building up in the box, or if the orange thing is bigger, it's the amount of heat that's being lost to the box. And when heat is being lost, when there's a net heat loss, the temperature will decrease. So heat energy is given by mass times specific heat capacity times temperature. So that's where you see that actually for a fixed, so C is a property of the material, and obviously M is a property of the mass of the little box, that heat energy is proportional to temperature. And if you look at that, it should be, looking at that, it should be in Kelvin, because if you're at 0 degrees Celsius, you're not at zero energy. You have to go the whole way down to 0 Kelvin. I'm assuming this is stuff you know about, actually, about Kelvin and stuff. So what we're going to do is we're going to say that the mass is density times volume. That's no problem to you. And so if we replace mass with this, and if we replace a change in, if it's a change in heat, the mass doesn't change, the volume doesn't change, the volume doesn't change, the density doesn't change. The specific heat capacity possibly does change with temperature, but we won't worry about that. So if there's a change in heat, it corresponds to a change in temperature. So the equation actually reads, and what's delta V is delta X, delta Y, delta Z. This is the equation. This is probably what you might call pretty much the heat equation. So on the left hand side, you've got a difference between the heat flow in and the heat flow out. And on the right hand side, you've got a change in heat inside in the box. So you divide both sides by delta V and delta T, and you get this formula here. Now, what you do then is you take a limit, you take delta X to go very, very small. That's basically making essentially making our wire or our rod one-dimensional, and delta T going to 0 as well, just to make it more accurate, because what's happening is, well, I suppose what's happening is the heat flux is changing in time. So if you make delta T very, very small, then the heat flux density is kind of constant then. So if you do this, that delta X and delta T both go to 0. The thing on the left is minus a derivative. And the thing on the right is rho C. And look, delta T over T, that's a time derivative. Now, if you use the fact that Q is proportional to the derivative of temperature, what that gives you is that if you can actually differentiate both sides of this, that the rate of change of Q with respect to X is proportional, and I can change the minus there to over here, is proportional to the second derivative of temperature with respect to distance. Now the constants are knocking around, so you got some kind of a constant on the left hand side in rho C. I don't know, do I actually tidy that up? Yeah, so there's an extra kind of term knocking around here. Well, there's not an extra term, but the K would be equal to, it's kind of the K dashed, which is the constant of proportionality here. Again, I'm assuming you know that proportional quantities are proportional if one is a constant time the other. So it'll be the constant of proportionality there divided by rho C. So that's where this K is coming from. And this is called the heat equation. So this is describes the temperature in the rod. And if you look at it, there's distance on one side and time on the other. So the solution is the temperature as a function of distance and time. So the distance is you picking a point along the rod, and the time, well, there has to be some starting time with some starting temperature. Usually we're going to think of the rod as initially 0 degrees. It comes in contact with heat sources and the temperature changes in time. So this is what we're talking about. So you just imagine the cold rod, and imagine you kind of affix it into the walls, and imagine both the sides of the walls are warm. Well, the rod's going to warm up, isn't it? And what we're interested in is both the final equilibrium temperature and the transient temperature as it cools up from 0 to the how we say equilibrium. So this is what we're looking at. Now we do have the tools to work with this differential equation, because we know that we can use finite differences to approximate this differential equation, and we will be doing that. I think there's a small note here. The 2 and 3D heat equations are the same, so all you have to do is you just add in extra terms. So you've got a, Laplace's equation, there's the second derivative of temperature with respect to distance plus second derivative of temperature with respect to the other distance, horizontal and vertical. You can do Laplace in 3 dimensions, so you just add second derivative of temperature with respect to the other direction, down, up, whatever it be. And if the material is isotropic, the same in all directions, then the K there is the same for all of them. Okay. And the other interesting thing is, look at that equation there. What's going on with the temperature when you reach equilibrium? Well, equilibrium is when the temperature does not change in time. So the object on the right here would be 0. So the second derivative of temperature with respect to distance would be 0. So looking at this equation on the bottom, imagine the right hand side is 0. Well, that's just Laplace's equation here. So Laplace's equation is actually just a special case of the heat equation. Right. Now there's some other stuff here. On page 79, we kind of saw this equation, and this is the steady state equation of an uninsulated one-dimensional rod. So there's heat. You've got the rod, but also the rod is losing heat to the air as well. How is the temperature in the rod changing with respect to time? Well, there is heat conduction along the rod. So that's this term, plus Newton cooling to the air, which is this term. And so for steady state, the time derivative, which is this, is equal to 0, and you get this. Okay, so that thing down the bottom, which we won't be doing, is another cool, well, I say cool, it's another thing that you can study. Okay, so what we have to do is we have to take this differential equation and approximate it using finite differences. So I'm just going to write down those formulas just up here, and then we'll start a new video then. So we have that the rough thing. So it's the derivative, first derivative is approximately next minus current over delta x, and the second derivative, and of course when you look at this, it'll be in a written assessment and it'll be open book, so you don't have to learn these off or anything, although even in an assessment I would give these formulas, of course. So the second derivative is next minus twice the current plus the previous divided by delta x squared. So we're going to use both of those in the next lecture to simplify the differential equation on the previous page.